This is a program about energy, which has always been an essential element in man's efforts to meet basic human needs. In antiquity, for example, the energy of the sun had been used to bake bricks and tiles and to evaporate seawater to produce salt. But in this program, we're going to concentrate on a prime energy source which was harnessed to turn the wheels, shafts and gearing of ingenious devices to supply water, food and clothing.
Long before water power was used, a technology of wheels, shafts and gearing had been developed, and which was moved by the muscle power of animals and humans. The lifting of water for drinking and irrigation purposes provides one of the oldest demands for energy, and as an example of man's ingenuity, the Archimedean screw is a good example of an ancient device which is still in use. In seeking to replace muscle power, man first turned to the obvious energy in a moving stream of water, and the water wheel, in its various forms, was the result. The common water wheel, that is the vertical wheel on a horizontal axle, was introduced into northern Europe in the 4th century AD, and by the time of the Doomsday Survey in the 11th century, 5,624 mills were recorded in Britain. All were water-powered and all used for grinding corn. Before exploring other applications of water power, we should first look at the water wheel itself. The vertical water wheel is classified into 3 main categories, depending on where the water contacts the perimeter of the wheel. If we take the clock face as an analogy, then if the water is introduced at 6 o'clock, the wheel is described as undershot. This is the commonest type of wheel and requires no modification of the mill stream itself, and only simple flat floatboards or paddles are required. If the water is introduced at 12 o'clock, the wheel is driven by the weight of water in buckets, and the wheel is described as overshot. The overshot wheel can only be used where there is sufficient fall between the head race and the tail race. The third category is described as breast shot, when the water is introduced anywhere between about 7 and 10 o'clock on the clock face. For a given quantity of energy in a stream of water, the question then arises, which of the 3 wheel types is best at converting water energy into shaft horsepower? This question intrigued John Smeaton, the 18th century British civil engineer, who, as a young man, experimented with a model test rig which he designed and built himself. He published his results in 1759 and showed that the overshot wheel was about 66% efficient, the undershot about half that value, and the efficiency of the breast shot wheel, as you might expect, lay somewhere between the two. As the water delivers its energy on the rim of the wheel and the power is taken off at the central axle, a stiff bracing is required to connect the two. 2 systems are commonly used. The first, with radial arms, is described as compass arm construction. The disadvantage with this system, when built in wood, is that the arms have to be mortised into the axle, which can seriously weaken it. The second system obviates this by having parallel arms which clasp the axle, which is left intact. The typical power transmission in a corn mill is shown here. The water energy is obviously collected at river level and has to be delivered to machinery on the upper floors. Fixed to the axle of the water wheel is the pit wheel, which revolves at the same speed as the water wheel. This engages with the smaller wheel, known as the wallower, and converts horizontal motion to vertical. Above this, the great spur wheel meshes with the stone nut to drive the runner stone through the bed stone. A good example of a working water-powered corn mill exists in Warwickshire. This is Charlcote Mill at Hampton Lucy, an 18th century building on the site of a mill mentioned in the Doomsday Survey. Its breast-shot water wheel takes its power from the River Avon. The wheel is started, controlled and stopped by means of a curved sluice. The water wheel is contained within the building, and it is centred on its iron axle by means of tapered wedges, typical of millwright practice. The wallower here turns at 2 3/4 times the speed of the water wheel itself. The great spur wheel and the stone nut transfer power to the millstones on the first floor. This is the heart of the corn mill, with grain from the bin floor above being fed into the hopper, and from there, by vibration, into the eye of the runner stone, which is turning at about 100 revolutions a minute. The stone ground flour falls into paper sacks for delivery to the customer. Fresh supplies of corn from the farm can be lifted up to the bin floor under the roof by the sack hoist, which is just one example of auxiliary equipment powered by the water wheel in the traditional corn mill. It was in the rural corn mill that the technology of water power was developed over the centuries by generations of millwrights. But the use of water to drive textile machinery in 18th century Britain led to the development of the factory in the Industrial Revolution, and was to change millwrights into engineers. Throughout the ages, the various processes of making textile fabrics from wool, silk and cotton were done by hand and at home, and the domestic scale of this activity was properly described as a cottage industry. But undoubtedly it was the mechanization and the use of water power in weaving and spinning wool and cotton fibres which characterized the change from cottage to factory industry. The principal steps in this mechanization are well known. In 1733, James Kay's flying shuttle dramatically improved the productivity of the weaving loom, and the spinning process became a bottleneck, as it took 5 or 6 spinners to supply just one weaver. There was thus a great incentive to improve spinning techniques. In the 1760s, James Hargreaves developed the spinning jenny, which had multiple spindles where the traditional spinning wheel had just one. Then, in the 1770s, Richard Arkwright applied the water wheel to spinning with his invention of the water spinning frame. By 1780, Samuel Crompton had perfected his spinning mule, and all was ready for a full-scale, water-powered textile industry. It is usual to think of the large textile factory building as part of the urban landscape of dark, satanic mills, but this was not originally the case.
It's often been said that Britain's Industrial Revolution began in the English countryside, and one of the best examples of a rural, water-powered 18th century cotton mill survives here in Cheshire. It is situated here to exploit the energy of the River Bolling, and it's Samuel Gregg's quarry bank mill in the village of Stile.
The original buildings of 1784 remain, and with later extensions, the mill is largely as it was in the 1840s. The energy centre of the mill is the water wheel, which the building straddles. The power of the wheel is taken by gearing and iron shafting to the various floors of the building, and then by belt drive to the individual machines. The water wheel at Quarry Bank Mill is of the type known as a suspension wheel, which was patented in 1805 by Thomas Hughes of Manchester. Here, the power is not taken off at the axle, but by a pinion meshing with teeth on the inside rim of the water wheel. A lightweight system of wrought iron spokes is used to stiffen the structure. The wheel is 32 feet in diameter, and this fall is obtained partly by the weir, which raises the head race, and partly by the lowering of the tail race. This required digging a tunnel 869 yards through the local sandstone to return the water lower down the River Bollin. From the mill pond above the weir, the water is delivered through a head race channel ending in a trough at the wheel itself. To control the quantity of water entering the wheel, a roller blind made of ox hide is used. As the blind is rolled down, water flows into the buckets and the wheel begins to turn. When the wheel ceased working in 1904, the minute book of the company said its slow and stately revolutions seemed the very embodiment of power and dignity. And indeed, within the huge wheel pit all is calm and peaceful, but on the floors above it is very different. Cotton spinning by the mule machine involves the same three operations required in hand spinning. They are, firstly, drawing out the fibres, then imparting a twist so that they lock together, and finally winding the thread onto a bobbin so that it can be used as the weft and warp in weaving. These machines revolutionized the spinning industry, one operator controlling hundreds of spindles. The power looms in the weaving shop at Quarrybank Mill were made possible and indeed are direct descendants of Kay's flying shuttle. And here again, one operator could control many looms. Whereas the first generations of textile machines were largely built by the carpenter, during the 19th century, increasing use was made of iron and steel, both in the machines and in the mill structures themselves. The iron and steel industry had long made use of water power to drive blowing engines for the blast furnace and tilt hammers in the forge. A working example of an 18th century water-powered forge can be found in South Yorkshire. Sheffield has a long history as a centre of the iron and steel industry, with a particular reputation for high-class cutlery and industrial edge tools. The city has numerous water streams and a local supply of gritstone for grinding purposes. On the edge of the city is the Abbeydale Industrial Hamlet, a metalworks taking its water power from the River Sheaf, which is dammed to produce a huge mill pond of 4 acres. The water here falls 20 feet between the dam and the river and is used to drive 2 water wheels. The works buildings of local stone are grouped around a central courtyard, and here they make scythes from wrought iron and steel. 2 of the workshops are of particular interest, the forge and the grinding hull. The forge was built in 1785 and contains 2 water-powered tilt hammers. The scythe blades were formed here by making a sandwich with a crucible steel core with wrought iron on each side. The 2 materials were welded together on the anvil under the tilt hammer. These rotating tappets on the main shaft engaged with the tail of the hammer, lifting it and then allowing the hammerhead to fall onto the hot metal on the anvil. The working of hot metal in the forge requires fires which are kept hot and bright by a stream of air from a blowing engine. Here the blowing engine is driven by its own water wheel. The engine has 2 cylinders, each 28 inches diameter, with reciprocating pistons with a stroke of 10 inches. The leather flap valves open on the downstroke and close on the upstroke to force air into the pipe, which delivers air to the fires. Circular motion is converted into reciprocating motion by means of cams and followers. In the forge are two typical examples of the millwright's desire to extract the maximum energy from a rotating shaft. On the main tilt hammer axle, a metal cropping guillotine is driven by a cam. And here, a belt drive runs a small grindstone. In the adjacent grinding hull, built in 1817, the blade of the scythe is formed in the traditional manner. From the noise and bustle of the metalworking industry, we come to the peace and quiet of the English country estate for a remarkable survival of water-powered woodworking machinery. This is done on Massey in Cheshire, the home of the Earls of Stamford since the 18th century. Here the ornamental lake of the gardens serves also as the mill dam and head race to power the estate mill. The building was completed early in the 17th century as the estate corn mill. It continued to grind corn until about 1860, when it was converted into a sawmill and estate workshop. It has been restored to working order with a remarkable range of woodworking machinery, powered by an overshot water wheel, 15 feet 4 inches in diameter and 3 feet wide. Power is taken from the water wheel by the drive pulley and belt drive to a line shaft on the floor above. Before starting the water wheel, it is necessary to engage the pinion on the drive pulley with that on the water wheel axle. Then the wheel can be started. The water wheel develops about 10 horsepower and drives the woodworking power tools used in fencing and maintaining a large country estate. At one time, the water wheel of this mill was also used to pump water up to the house for drinking and other purposes. Water wheels had been used in pumping for public water supply from the 16th century, but they were also used to solve an engineering problem associated with canal navigations. In planning a canal route, the 18th century engineer would obviously avoid crossing valleys and hills as far as possible. But if necessary, aqueducts or tunnels might be used. But more often, a flight or staircase of locks would be appropriate. When a canal boat uses locks to traverse a hill, water is drawn down from the summit level, and this water has to be replaced. The Kennet and Avon Canal runs from Newbury to Bath, and John Rennie, its engineer, designed a water-powered pump to lift water from the River Avon into the summit level of the canal. It is sited at Claverton near Bath and lifts water some 50 feet up into the canal. The pumping station started work in March 1813, and the water wheel is housed in the low building on the right and takes its power from the River Avon. And through gearing, a crank and connecting rods which drive rocking beams, the two water pumps are driven. And here the energy of the River Avon is used to lift Avon water up into the canal. The gear teeth on the pit wheel are made of wood and set into the cast iron wheel. This was common practice in the 18th and 19th centuries and was regarded as a safety device, rather like a fuse in an electric circuit. If the water wheel should suddenly jam, the wooden teeth would break, but they could be replaced more easily than metal teeth. The mill pond at Claverton can be isolated from the River Avon by means of a sluice on the mill leat. This pumping station, as with all the other examples in this programme, have used the energy of a stream flowing in one direction towards the sea. But in coastal areas on tidal rivers, water can be captured at high tide in a mill pond behind a dam. At about 1.5 hours after high tide, there is sufficient head to drive the wheel by opening the sluice in the normal way. The wheel will then run until 2 hours before the next high tide. When the rising water reaches the axle of the water wheel, it will cease to turn. Tidal water is admitted through sea hatches in the dam, which swing open on the flood tide and close on the ebb. This is the mill pond and sea water sluice of Ealing Tide Mill, situated on a tributary of Southampton Water. The mill dam across the river carries a toll road, and the 18th century red brick building is built on the site of earlier mills. It is the only surviving tide mill in the world to harness the energy of the tides for the regular milling of corn. The water wheel here has curved blades, and this simple early 19th century development doubled the efficiency of the undershot water wheel and led directly to the development of the water turbine. In this programme, we have concentrated on the harnessing of the energy of a stream of water as applied to corn milling, textiles, ironworking and pumping. When discussing the wider social and economic aspects of these technical developments, several approaches are possible. To some, it is the living and working conditions that are important. In many textile mills, for example, both the mill owner and the manager would have their own houses on the factory premises, and the young apprentices would spend the whole of their waking and sleeping hours at the mill. Another important approach is the study of the source of investment risk capital and the return in profit to shareholders. But the principal characteristic of the Industrial Revolution, and which brought about the change from cottage to factory industry, was the replacement of manual labour by water power.
As we've seen in this programme, once you have the axle of a water wheel turning, the power takeoff can be applied to a fascinating range of industrial processes. The oldest of these, of course, was the milling of corn for flour. In fact, in Europe, it isn't until the late 12th and early 13th century that it's possible to find a reference to any other type of milling. And from that time, in industrial terms, for 500 years, water reigned supreme.